gives us an error saying, yeah, something's wrong. We're going to run a script. UPX is like the most common packer, and it's pretty simple. So this script basically executed the program and dumped us at OEP. Note the address, 40BB09. That's the original entry point address. So keep that in your mind if you can, because we'll need it later. So now we're going to dump the process memory to a file using load PE. So that's dumped. And we're fixing up everything, making sure it's okay. Here's import reconstructor, import rec. This tool is going to help us rebuild the import so we can see what the capabilities of this file are. Import rec is sort of like black magic. You have to really fiddle with it to get it to work. But right now what it's doing is it's enumerating all the imports it can find in memory for this process. And then it's going to apply them to the file we dumped earlier. Okay, now we're going to open this dumped, deobfuscated file in IDA. And we should see a totally different view of it. So this time we don't get the same error when IDA starts up. Blue means code. So basically if you start seeing blue, it means you have good valid disassembly. And here we have imports where before we had nothing. The names window is populated. So this is an example of a simple packer and how you go through deobfuscating it so that you can analyze the malware. We got all the functions. We have actual disassembly that makes sense. You can see a bunch of functions here. So that's that.
Okay, so what? All of these, this is just a manual implementation of watching for a write into memory and then an execution into where that memory was written. That's the algorithm that are implemented in all these bugs here. Our point is that there should be a generic way to debug or an easier way to actually get this information out. So we need something that actually modifies the operating system at the fundamental level. Basically, it should be generic, work across all executables, efficient, good, and not degrade your system too much when it's not running, and as much as possible be undetectable and extensible. So we'd like to script all this up. So again, the algorithm, track all the memory that's written. If you see an execution into that memory, it's unpacked, right? That's a good candidate OEP. So the things that you have to be able to monitor are memory writes and memory executes. And next thing we want to do is automate the process. So there's a general method called dynamic instrumentation. This basically allows a running process to be monitored. The program that we chose to implement this in is Intel's PIN. Don't ask me what PIN means. I'm still trying to figure it out. If anybody knows, shout it out. But this uses a just-in-time compiler, very similar to Java, to actually instrument the code. So basically, you can get a variety of different controls. You can control execution at the instruction level. You can look at memory accesses, and you can also look at basic blocks. So you find process, attach, and detach. So if we take our example code here, our nice page of assembly, this is what it looks like normally executing. And what PIN does is it'll actually insert instructions before and after each execution. So the modified instructions look like this. This is just our original code interspersed with the new the PIN instructions. So what our implementation does is that we monitor all the memory writes and insert them into a hash table. And if we get a hit on that hash table during execution, we call that a candidate OEP. So the results are, it's pretty successful for the most commonly used packers. Essentially what PIN does is it inserts itself into memory. So as if the process does any self-introspection, it's going to find PIN and die. But we found it works on roughly 70% of our collection. And here's a nice pie graph of our collection.
You can see UPX is the most common one.
Right. It works on ASPAC, FSG, PCompact, and UPX. The way that we tested this is to create a simple Hello World application. We mapped this out in a tool called Orias's GDE, which is Go Visual Diagram Editor. If anybody's used GraphWiz, it's a version that works on more than 10 nodes. So this is an actual Hello World application in Windows. Each one of these little tiny unreadable boxes actually contains a memory address, and you have to trust me on this one because it's hard to zoom in. But what's neat is it kind of makes a pretty picture, and basically what I was trying to do visualizing this is find the unpacking loop. So throw a shmoo ball if you want at it, if you can identify it. Okay. But it's right down there at the bottom. Basically, this is a tightly compressed, adjacent located list here. And if you look back at the original slide, that's down on the bottom right there. But it really jumps out at you. So this was a good proof of concept of the algorithm that had been in a couple papers. We manually identified all the addresses that we found. The graph there, you can see the clustering and actually zoom in on the unpacking code. And what's nice about PIN is it allows you to detach from a process once you've attached. So there are some problems with the dynamic instrumentation method. First of all, it's extremely detectable. Memory checksums, it shows up. Signature scanning, it's going to show up there. It's difficult to use, and really sorry about that. It was just a proof of concept code, but it's a code that we published at Black Hat. Some people had trouble with this. But basically what we want to do is extend this to work generically and non-detectably. The other thing is that if you're inserting instructions before all the other instructions, it's going to slow things down considerably. So we need something faster. So the solution that we need to go to is a core operating system component that monitors all memory, intercepts that memory access, and logs it. And it would be really nice if it was a fundamental part of the operating system so we didn't have to worry about being detected. The method we chose is to overload the memory management unit. So we're going to go into real quick how virtual memory works on Intel, but each on modern operating systems. So Intel has a method where each process can have its own memory, and that's called virtual memory. And the idea is to keep other processes from being able to read each other's information. So this virtual address needs to be translated to a physical address, which is the actual address on the chip of RAM. A non-PAE mode 32-bit processor uses 2-page indexes and a byte index, and each one of those has its own page directory. So if we take a sample virtual address, the first thing that happens is that the CPU references that memory. So we split that off and find the virtual page number, which is the first 20 bits. The CR3 contains a pointer to the page directories, and that first page directory index is an index into here, and that gets you the page frame number. The next thing that happens is that the page frame number goes to the page table entry, and then the second offset is used. And then finally, you actually get to the page that's in memory, and memory is pulled out. So this process is usually performed by hardware in the CPU. Each one of these data structures back here has various permissions, whether you can write to it, whether you can read from it, execute from it nowadays, whether it's present, and this special field called a user mode. And by user, what Intel means is the operating system. So this process is a little bit slow, and to speed that up, another hash table is implemented in hardware called a translation Lookaside buffer. So this is a major source of optimization in modern computers. So the hardware resolves as much as it can of the address as it can. If it gets to something it can't handle, then it invokes the page fault handler. So for instance, if you have a page of memory that's not loaded in RAM, or it has incorrect privileges, or it's loaded but it's mapped with demand paging, or it's not legal. Like for instance, if you dereference a null memory address or a string of 41, 41, 41, that typically invokes the page fault handler. So it's all indicated by special fields. Intel goes further. They define two TLBs. The first one is a data TLB. This is when you actually access a pointer in memory. The second one is a instruction TLB. Basically, this is for quickly executing code.